up to this point in our discussion on pressure, we really haven't mentioned any type of devices or instruments that we can use to help us measure that pressure. So let's suppose we have a certain container, and inside the container we have air molecules, and we would like to calculate the pressure inside the container due to those air molecules. Now, one device or instrument that we can use to help us measure the pressure is called an open tube manometer, and it looks something like the diagram here. So let's suppose this is our container and we want to calculate the pressure due to the air molecules inside our container. Now suppose this container is connected to a tube and the tube is open at the other end. It's open to the atmosphere. So the pressure at this end is the atmospheric pressure P naught, and the pressure inside this container is given by the value P. Now, let's suppose that this end of the container is sealed for the time being, and we place a fluid, let's say mercury, inside our container. Now, because the pressure here and the pressure here will be exactly the same, the change in height between this level of mercury and this level of mercury will be exactly zero, because the pressure here are exactly the same. Now, what happens if I open this section of the tube? Well, if I open that section of the tube, what happens is my air molecules found inside my container will escape and will travel to this side of the mercury. And let's suppose that the pressure inside the container is higher than the pressure of the atmosphere. And that means when my air molecules escape, they will push the mercury more than this atmospheric pressure will push the mercury from this end. And because the pressure is higher from this end than from this end, because we assume the pressure here is higher, that means the pressure due to these air molecules found in the container will push the mercury a certain distance change in H. So let's suppose this change in H is given by this distance here. Now we can calculate, using the difference in pressure, what the actual pressure inside the container is. So we can calculate this difference by simply using our equation for constant density. So we assume the density of the mercury is constant, so that means using this change in H, we can calculate the pressure difference by simply taking the product between the gravitational constant G, the density of the mercury, and the change in H. So this is the pressure difference between our pressure inside the container and the atmospheric pressure. Now, the atmospheric pressure we usually know. The atmospheric pressure at sea level is 1.013 times 10 to the 5 newtons per meter squared. So using this atmospheric pressure and the difference in pressure between these two areas as calculated by this section, we can use the following equation to actually calculate what the pressure inside our container is. So the pressure inside the container P is equal to our atmospheric pressure P naught plus our change in pressure due to this quantity. So our density times the gravitational constant times the change in height. So let's look at the following example in which we're going to utilize the open tube manometer to calculate the pressure inside the container. So, an open tube manometer is used to measure the pressure in an oxygen tank. So let's suppose this is now our oxygen tank. If the atmospheric pressure is 1013 millibars, what is the absolute pressure in pascals inside the oxygen tank if the height of the mercury in the open tube is A, 20 centimeters higher than the other end, and B, 5 centimeters lower than the other end? So let's begin with A. So 20 centimeters higher at the other end simply means that this end is 20 meters higher than this end. So that means the change in H is simply 20 centimeters. So let's begin by converting 1013 millibars to pascals. So recall that 1013 millibars is simply 1.013 bars. And 1.013 bars is equal to 1 atmospheric pressure, which is in turn equal to 1.013 times 10 to the 5 pascals. So now we can use this quantity and this formula to calculate the absolute pressure inside our oxygen tank. So P equals P naught, our atmospheric pressure given by this quantity, plus our density times G times change in H. Our change in pressure when we go from this amount, or from this location to this location. So we know that our mercury's density is 13,600 kilograms per meter cubed. We know that G is 9.8 meters per second squared, and we know that our difference in height is 0.2 meters. So we multiply these out, we add up the two quantities, and we get an absolute pressure inside the oxygen tank of 1.28 times 10 to the 5 pascals. Now, let's look at part B. So now suppose there's a 5 centimeter difference, but this end is higher than this end. Because this end is higher than this end, that means the atmospheric pressure must be higher than our pressure inside the tank. So instead of using the plus sign, we must use the negative sign because the change in height is negative. So the pressure inside the tank is equal to the atmospheric pressure minus our gravitational constant, our density, and our change in height. So we have the same exact quantity for P naught, but now instead of using 0.2 meters, we use 0.05 meters. So we multiply this quantity and we subtract it from our atmospheric pressure, and we get a pressure of 9.46 times 10 to the 4 pascals. So the fact that this quantity is lower than atmospheric pressure makes sense because this end is slightly higher than this end.